We recording? Yep. All right. Okay. Welcome to Structural Analysis Lecture 3. Before I get into the specific announcements, which really aren't that many, I did get a lot of TA requests. I really appreciate it. I got more than I thought I would. So I have to go through and pick. I'm going to be sending some emails out later today, but I will keep you all posted. So just if you sent me an email, just be on your lookout. That's all I'll say. Same thing with the research stuff I mentioned on day one. It's been a very crazy week up in the dean's office, I'll just say, with everything. So, okay, we're going to get right into it with our first, what I'll call real topic of the semester, which is support reactions. For those of you that had me for statics, and even if you didn't have me for statics, this is something that you start looking at near the end of the class. And what so I guess what I would say is if you have a good refresher or a good memory of your statics class, some of this will be a little repetitive, but what I'm going to do is I'm going to start slow and work my way up, as it were. So we're going to start with some really basic examples, and then by the end we're going to have internal hinges and concentrated moments and triangular loads and all sorts of crazy stuff. But we take it slow and work our way up. Now, this is arguably the first task in any structural analysis course, and I'd argue it's one of the most important because everything that you do in a structural analysis setting in terms of identifying response for the purposes of design, ensuring that your structure meets serviceability limits, et cetera, it tends to always start with this. The idea is that you're trying to determine the external support reactions that keep your structure in equilibrium. And from those, you can then determine shear and moment diagrams, axial forces and trusses. You can determine how much the structure is going to deform. We can start looking at influence lines, which is I haven't really mentioned influence lines. That's a really wild topic that we will deal with near the end of the semester. That's a tool that you use to assess a structure that's subjected to loads that move. Does anybody know what type of structures we would deal with where the loads move? Bridges! I'm a bridge engineer, and by God, you are going to learn something about bridges in here. So that's just how it's going to be. But it always tends to start with support reactions. And so the way I like to go through this is you've done these types of problems before, but it probably has been a little while. So we're going to start off with some pretty basic problems, and then we're going to ratchet it up slowly. And by the end, we're going to be dealing with some pretty wild structures. But the idea is that if you can handle a simple problem and you understand the tools necessary to analyze a simple structure, it really isn't any different. It's all sort of the same. It's just different loads and different geometry, but the process is the same. And we're going to be using our just trusty, familiar equations of equilibrium. Sum of forces in the x direction, sum of forces in the y direction, sum of moments. Now, before I get into our first example, which this is going to be our first example, one of the things I want to mention right off the bat, and it's something that we're going to be dealing with for a while. If you remember, our last lecture was all about classifying structures and all about determining the degree of indeterminacy. And we found that structures that are stable and have an I value of 0 are statically determinate, correct? So the point I'm making is that for a good little bit in here, we are exclusively going to be analyzing structures with an I value of 0, so the structures that are statically determinate. And the reason for that is, well, number one, not really much use in analyzing unstable structures, because I don't know about you, but I really don't want to be building any structures that are unstable, so there's not really any point there. Plus, there's not really any way of analyzing it beyond looking at, rigid body dynamics or whatnot. But structures that are statically indeterminate, which, to be clear, we do build quite a few structures that are statically indeterminate. In order to analyze those, you must first understand how to analyze statically determinate structures. In fact, a lot of the methods that you use to analyze statically indeterminate structures are predicated upon a fundamental understanding of determinant analysis. So like, for example, if you have one too many supports, that might be an indeterminate structure. Well, one of the methods that you can use to analyze that indeterminate structure is recognizing that the deflection at that support is 0. So you have to be able to analyze determinate structures, understanding their forces and deflections and so on and so forth. So it always starts here. So we got a really basic problem. We have a beam that has some concentrated loads on it. We're going to determine the reactions on this simply supported beam. Just about every single example that we will do, both in the homework and in the class, we use US units. We're going to be using kips, feet, inches, so on and so forth, because we're civil engineers, and that's what we use, in the field. So let me pull up my notebook, my handy-dandy notebook. I have a 2.5-year-old, so I'm sure I'll throw a Blue's Clues reference in there somewhere. Okay, so here's our beam. So let's look at our support conditions. We have a pinned or a hinge support on the left. We're calling that support A. And then support B, we have a roller support. So if you remember, how many reactions does a pinned or a hinge support have? 2. And how about the roller? 1. Okay. So the first thing we need to do is we need to identify those reactions. And what I'm going to do is I'm going to draw those reactions in an assumed direction. So I'm going to assume, for the sake of discussion, that both of these vertical reactions, and we'll draw those like that. I usually put a little tick mark through the reactions to indicate that those are forces I don't know. Those are unknown reactions. I'm going to draw those acting upwards. Now, my common sense is telling me that if the loads are going down, if I have a beam and I'm pressing down on it, then the supports have to press up on it to keep it in equilibrium. I think that just makes sense to everybody in here, and that's a pretty easy to understand. For this problem, that's basic. We're going to be dealing with some pretty weird beams in here, and sometimes it isn't that easy to see. If you've got overhanging beams and hinges and concentrated moments, your guess might be as good as mine before we start doing some math and doing some analysis. So what you want to do at the very beginning is just assume a direction and keep that consistent in your analysis. And if you get a positive answer, that just means your assumed direction was correct. If you get a negative answer, again, doesn't mean you did anything wrong, or the problems, you got to start over from scratch. All that means is that your assumed direction was incorrect, and so if you assumed upward, you got a negative answer, the reaction's downward. And that happens both in some of the problems that we do in here and even in real life. So I'll assume these reactions are upward. This is a hinge support. It has a horizontal reaction. I'll just assume that acts to the right. Now I'm going to need to name these reactions, so I'll be pretty simple. We'll call this AX. We'll call this AY. We'll call this BY. Okay. So what I can then do is utilize my 3 equations of equilibrium to solve this problem. So just going back to tethering this to what we did last time, we have 3 reactions, so our R value is 3. We don't have any internal hinges, so if I compute my I value, I'll get a 0 value for I, and this structure then would be stable and statically determinate. And what statically determinate means, if you remember, is that I've got 3 equations of equilibrium, sum of forces in the x direction, sum of forces in the y direction, and sum of moments. I can use those 3 equations of equilibrium to solve for these 3 unknowns. Okay, so let me write these 3 equations of equilibrium here up top just so that I have them. Sum of forces in the x direction is 0, sum of forces in the y direction is 0, and sum of moments equals 0. Now, again, so far, I think that it might have been a while since you've done this stuff, but this should all be pretty familiar to everybody in here. Am I correct? Okay. So what we need to do is we need to utilize these 3 equations of equilibrium to solve for these reactions. Now, we can do this really in any order that we would like, and we can do it really in any fashion that we would like, but we can also be strategic and use a little bit of common sense in order to make the math a little easier for us. For example, the sum of moments expression states that the sum of moments about any point in the system equals 0. Okay? Now, if I want to make the math a little easier for me, what I'm going to do is sum moments at a point where I've got quite a few unknowns intersecting. And why do I do that? Well, the definition of a moment is a force acting upon a point at a given distance or at a given moment arm. And if I sum moments with my unknowns intersecting at that point, the distance is 0, right? So the moment's 0. So what I'm going to do is I'm going to sum moments at A. I'm going to sum moments at support A. And so if I sum moments at support A, this support reaction and this support reaction are going to be acting through A, so I don't have to consider those when I sum my moments. So I can sum moments at A and use that expression to solve for the reaction at B. Everybody okay with this, that concept? Okay. All right. Now, I'm going to show you something which, if you had me for statics, I think I showed you this. If you didn't have me for statics, this is going to be a little bit of a new way of doing it. I'm all about making the problem as simple as possible. I'm all about keeping things straightforward. Whenever you're summing moments and stating that the sum of moments equals 0, another way of stating that is that all of the moments that act clockwise have to equal all of the moments that act counterclockwise. Okay? So one of the ways that I do this, especially when you have beams that have a lot of loads on it, I find that this is pretty straightforward, is I like to draw myself a little table. And I'll put all the moments that act this way and all the moments that act this way. I'll just lump them on either side and just sum everything up over here, sum everything up over here, set them equal to one another. And I think you'll see that this is pretty simple and pretty straightforward. So if we're starting off, we're summing moments at A, okay? I don't have to consider AX and AY. So let me show you how this works. Let's start off with the 20 kips. Let's do this one together. Does that 20 kips, does that generate some bending moment at A? Yes, it does. Okay, so if I'm at A, and this is the 20 kips, it's wanting to rotate that in this fashion, right? So that means the 20 kips would be on this side, right? Now how far, what's the moment arm that 20 kips is from A? 6 feet. So what I'll do is I'll write 20 kips times 6 feet. And I'll write that over here. That's just my little shorthand. The little K is for kips, and the little tick mark, that's for feet. So 20 kips times 6 feet. All right. What about the 30 kips? Does the 30 kips generate moment at A? Yeah. Yes. Okay. Does it belong on the left side or the right side? Left. And what is the moment arm? 15 feet. There you go. See? It's like riding a bike. So 30 kips times 15 feet. All right. What about the 18 kips? Generate moment? Yep. Does it generate moment? Does it belong on the left side or the right side? Left side. And what's the moment arm? 22. There you go. Not too bad, right? It's pretty straightforward. All right. 18 times 22 feet. Now, am I missing something? The BY. I don't have to consider the AX and the AY because they go right through A, but the BY generates moment as well. Which side of the table did it go on? The right side. Okay, and what's the moment arm? 30 feet. Okay, so there you go. So we have BY times 30 feet. Now, so how do we do the math? The math is pretty simple. So I look at everything on the left. What do I have? 20 times 6. What is that, 120? 30 times 15, what is that, 450? 18 times 22, what is that, 396, I did that right? You should have your Casio FX115 ES Pluses, right? There we go. Who didn't bring their Casio FX115 ES Pluses? Shame on you. All right, so 120 plus 450 plus 396, the 120 and 450, that's 570. What do I got? 6. That 966? Did I get that right? I think that's right. 966. I have a second on that. Good. Okay, so that's 966, and the units for that are foot kips. So remember, moments are forces times distance, so 966. And I tend to write moments in two different ways. I might write 966 foot kips, or I might say 966, and I might go foot kips like that. I might just go tick mark and then K because I'm lazy. All right. Everybody with me so far? And then that's going to equal by times 30. And so to solve for by, all I do is divide by 30. So what's 966 divided by 30? 32.2. Do I have a second on that? Good. All right. I usually do that. I'll ask, and then I'll ask for a second to make sure everybody's engaged. So if I solve this, I get by is positive 32.2 kips. And that means because I got a positive number that I assumed the correct direction. I assumed that that was acting upward. That was correct. So my reaction is 32.2 kips acting upward. So far, so good? So what I also want to do before we move on is I want to go back to this little box up here. And I want to recognize I did exploit one of these expressions. I exploited the sum of moments equals 0. So I'm going to cross that one out. All right, I already used that one. Okay, I got two more. Sum of forces in the x direction, sum of forces in the y direction. I'll let you pick which one you want me to do first. X. Okay, so let's do sum of forces in the x direction. So now, if you want, what you can do is you can draw yourself a little table and you can say everything going to the left and everything going to the right. We'll do it formally this time just for the heck of it. So we'll draw a table of everything to the left, everything to the right. I don't need to worry about that because that's vertical, 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 vertical. I've got AX going to the right. What do I have going to the left? Nothing. So AX is 0. You don't need to get super formal on homework like this, but I do want to see AX equals 0. I do want to see that you utilize the sum of forces in the x direction to indicate that AX is 0. What I don't want you to do is just ignore it, okay? Because for a great many structures, there will be a horizontal reaction there. And if you don't go through the process of determining what that reaction is, it's going to cause some problems on the statics to come. So for instance, if you're doing a truss analysis and you don't determine that horizontal reaction and you start doing method of joints, you're going to have a bad day because nothing's going to match up and it's going to drive you crazy, okay? So far, so good? All right, so we exploited sum of forces in the x direction, so the only thing left is sum of forces in the y direction. So what I do is I do a similar table and I say all the sum of forces in the y direction states that everything going up's got to equal everything going down. So put everything going up on the left, put everything going down on the right, and just list them up and add. And by the way, you don't have to do it this way. If you want to write out the equation, that's fine too. I'm not going to be nuts on the format. As long as you're doing the method appropriately and you get the right answer, I'm fine with that. So I'm easy to get along with. So let's start listing these down. So AX, is that going to go in this table? No, because that's a horizontal force. AY, that's going to go up. BY is going to go up too, but we know what that is. So what I might do is I might say AY, and I might say BY, but we know that's 32.2. And then for everything going down, 20, 30, 18. So everything going up, it's got to equal everything going down. AY plus 32.2 kips equals 20 plus 30 is 50. 50 plus 18 is 68, so 68 kips. AY again comes out positive, and 60 minus 32.2 is 35.8. Do I have a second on that? There we go, 35.8. And because I got a positive answer, that means that is going upwards. So what I kind of like to see on the problem, so I guess, we've used all three of our expressions. What I kind of like to see at the end, and I scrolled down a little bit, is I kind of want to see a summary. So we know that AX is 0, AY is 35.8 kips going up. BY is 32.2 kips also going up. And then maybe circle that and say answers. So that makes grading a whole lot easier. The problem is that what are the reactions? Those are the reactions. Sorry, those are the reactions. That's the answer. Is that shaking the rust off a little bit on those statics exercises, those statics muscles in your brain? Not too bad, right? All right, I'm going to stop for a sec, see if anybody has any questions. Everybody good?
You like my shirt?
There's nothing civil about this engineer. I don't trust you. I'm a dork. It's okay. I do have a fair amount of dad jokes that I'll throw out, throughout the semester because I'm a dork. What's a pirate's favorite letter? You'd think that, but their real love is the sea. Again, I'm a dork. Just y'all are gonna have to build up your resistance. It's gonna be a long semester. Thank you. Okay. Sorry.
Trying to buy your love.
Oh, just wait. It'll get a lot worse. So, all right. So, what I want to do is I want to take this problem. Okay. I want to take this problem and ultimately I'm going to complicate it a bit. Okay. And so, from problem 1 to problem 2, you can see we've made it a little different. So there's a change in the boundary conditions. There's also a change in the type of loads. Now we've got point loads and these triangles and distributed loads. What's going on with that? So let's go back a little bit. Okay, so the previous example employed concentrated loads. So if you ever hear me use the term concentrated loads or you hear me use the term point loads, that's kind of the same thing. Now, where point loads show up in real life is usually either like a heavy concentrated load on a structure or when elements frame into one another. So if you have beams framing into other beams, the end of that beam sort of distributes that load as a concentrated load, that reaction. But probably the most useful of loads, or the ones that I could say are almost universally used in any structural system, is a distributed load. So instead of lumping the load at a single location, it may be spread out over a given area. And so let me give you sort of a real-world example of this. So let's say we were structural engineers in charge of designing a big, hotel or conference facility. And there's a big ballroom or a big conference area. We are not going to design these beams for 2,000 point loads for each of the people in the room. We're not going to do that. That doesn't make sense. Okay? What we're going to do is we're going to assume basically a pressure load over the entire floor system. And that pressure load is going to be representative for what the floor is used for. Okay? So sometimes if you ever hear me use the word dead loads or live loads being what the structure is used for, I might instead refer to live loads as occupancy loads because the live loads represent what the structure is used for. Let me give you another example that'll hit a little closer to home. When you are designing a building like this one, like the Weisberg Applied Engineering Complex, so what the structural engineer will do is they will design the classrooms for a live load usually of around 40 to 50 pounds per square foot. And that live load is meant to simulate you and me, the desks, the computer, what the room is used for. Okay? Now the hallways might be designed a little differently. The hallways might be designed for 80 pounds per square foot. Why? Because when class lets out, there is a more dense concentration of people in the hallways than there is in the classrooms. Also, what happens if we have a fire alarm? Then the hallways are really going to be packed, right? There's going to be more people there, so we design those a little bit heavier. So school facilities, hotels are designed like that. The rooms have a different load than the hallways. If you design a commercial office building, if you've ever been in a big office building, like cubicles, like think Office Space or something like that, what they do is the developer, the structural engineer, might design the entire floor as if it's one big hallway, because the developer wants to be able to slice off certain components and rent it out to lawyers or dentist's office or whatnot at X dollars per square foot, and they don't want to be restricted by where the halls are and where the rooms are. So they might just design the floor system as one big hallway. That's actually pretty common in spec office space. If you're designing a library, you design the floors for something like 150 pounds per square foot. Why are libraries so heavy? The books, yeah. Books are pretty heavy. So the load changes depending upon what the structure is used for. And so what might happen is the floor system sees the load as a big pressure, but each beam is seeing that distributed as this uniformly distributed load. And yes, sir?
Are there like set loads for things, or do you have to figure that out?
That's a great question. So the question was, are there established loads, or do you have to figure that out? So the short answer is yes, there are established loads. We talk about that a little bit more in some of the design courses, like steel design or concrete design, when we really start getting into the details. One of the most common guides that we reference in engineering is a guide called ASCE 7. So ASCE does more than just student competitions and concrete canoes. They are a large professional organization, and one of the things that they do is they convene a series of technical committees that publish documents to make decisions like that easier for you as an engineer. And so ASCE 7 publishes standard loads that you would use for office buildings, theaters, hockey rinks, whatever. Now, what may happen, and it's possible, especially in the building design side of things, is you might be working for a particular client that's, okay, I'm designing this, I need a particular type of museum, so we're going to use this load. Okay, we'll use that load. So the two places it might come from is either a guide like ASCE 7 or the client. The client may spec out the load. That's usually pretty rare. See, as a structural engineer, designing buildings and designing bridges are really different from the clientele that you interact with. See, if you're designing a bridge, who's your client? The state, right? And who works at the State Department of Highways? Engineers, right? So you can speak engineering to your client a little more effectively than you can in building design land, because your client in building design land is either going to be the architect, right? Or if you maybe work at an A&E firm, your client may be John Hancock Insurance Company. And John Hancock Insurance Company, they don't care if the building's made out of steel, concrete, popsicle sticks. They don't care. They just want a building, right? So it's up to you as the engineer to figure that out. And unless you get direct, guidance from the client, that's where guides like ASCE 7 come into play. That's a really good question. So it's a really great question. Any other questions? This is good stuff. I like this. This is great. Okay, so the beams might see the load as distributed loads, and so then you get those reactions, and then maybe these beams on the end see the reactions as point loads. That kind of gives you a big picture of what's going on here. So the most common types of distributed loads that we deal with are either uniformly distributed loads like this, or triangular loads. And I can see some of you thinking, oh, come on. We don't see triangular loads in real life. Yeah, you do. You do have to deal with them. And I can give you two examples where you would see them in real life. Okay? The first is looking at hydrostatic effects. This is something that you'll learn in one of Dr. Waite's courses in fluids, where if you have, if you're looking at fluid forces, the pressure linearly varies with the depth. So if you're looking at a dam or looking at a retaining wall or something like that, the distribution of load on that element is going to be triangular in nature. It's going to linearly increase as the depth changes. One that is a more purely structural engineering example of triangular loads is snow drifts. So what happens is, how many of you all have ever been on the roof of a commercial building, like a roof of a building like this? Has anybody ever been on a roof? Are they like this, or are they flat? They're pretty flat, right? I mean, there is a very minor slope there for drainage and whatnot, but they're largely pretty flat. And so, is it? Let me ask you this: can you just step off and woo, or is there a little barrier? Usually a little barrier, a few feet high, right? Well, let's go back in a time machine 6 months ago. Anybody remember 6 months ago that lovely storm that we had? So what's going to happen is you're going to get a lot of snow on the roof, right? Now, doesn't wind accompany snowstorms? And so you get a bunch of snow on the roof, and then the wind blows. The wind bunches up that snow along one of those walls or along one of the appurtenances, and suddenly, by golly gosh gee, you have a triangular load. So that is a real example of triangular load distribution. In fact, the code specs out, ASC 7 that we talked about earlier, it specs out for given geometry you have to analyze for these conditions. So that is a real example of triangular distribution, and doing that, it's a little bit of a process because you have to determine your ground snow load depending upon where you're at in the country, and then convert it to a roof load, and it's a thing. That'll be something we talk about in some of our design classes later. But just wanted to illustrate that this is real world stuff. Now, how do you handle that from a reaction standpoint? Well, the way you handle that from a reaction standpoint is you break out your old friend, the centroid, okay? So if you remember, the centroid is the place where you can idealize that area or that region as a single concentrated effect. Because if you collapse that load into a singular concentrated load at the centroid, it meets both force and moment equilibrium. So for a uniformly distributed load, you can sort of think of that as a rectangle. So the concentrated load would be the area of that rectangle, the magnitude of the load times the length, and then it would act right in the middle. And that's the centroid explanation. I mean, the real world explanation is pretty simple. So if I look at, let's say, this previous slide, if I have 1.5 kips per foot and it's over a distance of 12 feet, how much load is that? 1.5 times 12, right? And where do I idealize it? Right smack dab in the middle. So that's a pretty straightforward analogy. For triangles, same idea. What's the concentrated load going to be? It's the area of the triangle, 1/2 base times height. Where is the centroid of a triangle? If this is L, remember it's 1/3 over from the big end. Remember that? Centroids for triangles are 1/3 of the way over. Now, so what we're going to do, I just want to show you what's going to happen here in a second. What we're going to do is we're going to take this problem and we're going to take these distributed loads and turn them into point loads. And then it's going to become the same problem we just did. But I want to be crystal clear. This technique only works when you're trying to determine equations of equilibrium for computing, reactions. Any time that you're looking at, let's say, drawing shear and moment diagrams, or you're looking at cutting sections and whatnot, especially if you're cutting sections through the loads, you can't do that. You have to revert back to the original load. This is really just a shortcut to writing the equations of equilibrium. Makes it a little easier for us as engineers. Now don't worry, we're not going to have to draw shear and moment diagrams for a little while. That's going to be a task after the first exam. But when we get to that time, that's going to be sort of monopolizing our lives for a little bit. So I just want to plant that seed in your head for later. Everybody good so far? All right, so let's look at example 2. So we're going to compute support reactions of this beam, and we've got different loads going on. We've got concentrated loads, we've got triangular loads, distributed loads. So already it looks more complicated than the last problem, but the whole point of what I'm talking about is that it's not more complicated. It's the same idea, same principles, same concepts. All right, so I do not want to keep my ink annotations. All right, so let's go back here. Which there was a question earlier. If you go to the class notebook, I want to show you something. If you go into the content library, you can see that I've got a different page for every example, so it's not going to be one stream of consciousness notebook. So if you're looking for a particular example, you're not going to have to, go like crazy to try and find it. You can, if you want reactions example 2, just go to the page. It's right there. Okay, So we're going to draw the, so we've got the free body diagram. We're going to draw our reactions and all that stuff here in a second. Let me make this bigger. Some of you are drawing this out. I'll give you a minute. I'm not going to be the guy who's like, let's go, let's go, let's go. Now, if you need a sec, take a second, you know. Y'all are paying cash money to be here. I want you to get your money's worth. Again, whether it's scholarships or loans or whatnot, y'all are paying cash money to be here, and I want you to get your money's worth. So again, if you got questions, ask them, please. I want to make sure that you all are understanding what's going on. One of the things about this class is it does build on itself. If you don't understand support reactions, then truss analysis is going to be kind of tough. And if you don't understand truss analysis, computing deflections and trusses is going to be even tougher. So please, if you have questions, ask them. All right. Y'all need another minute? I can give you a sec. Everybody good? Okay. All right. So we've got our problem here, and we're going to determine our support reactions. We have similar boundary conditions than we did before. So we've got the hinge or pinned boundary condition, and we've got the roller boundary condition here. So I'm going to do what I did before and draw vertical reactions like that. So we'll call this AY and BY, and we'll do this. We'll call that AX. But let's be clear. What's AX? Same thing. AX is 0. There are no lateral loads. So what I'll do over here off to the side is just say sum of forces in the x direction is 0. AX is 0. I'll just keep that simple. I want to see you go through that, but you don't have to be super formal. And no need to list out your system parameters or anything. Did I say that? Okay. No, I'm not being recorded. Okay. All right. So we've got our unknown support reactions illustrated. One of them we've already solved for using sum of forces in the x direction. Now we've got these loads. What I want to do is I want to take these loads and I want to make them easier to deal with. I'm going to start with this distributed load over here. I've got 1.5 kips per foot, and it is being distributed uniformly over a length of 22 feet. So how much total load is that? $33 kips. Okay, so what I'm going to do is I'm going to do something like this. I'll draw a little dotted line. 33 kips. Okay, and where is that? Like, how far is that from this free end over here? 11 feet, right? Because it's a rectangle, so halfway over. So $11 feet. I like to be kind of color coordinated with my diagrams. I use green for dimensions. Again, if for some reason you can't read anything, let me know. Okay, so now I've got this triangular load to deal with, or this load that's linearly distributed. So help me out. How much load is that? How much total load? So it's 15 feet wide, and it goes from 0 to 2.4 kips per foot. What's that? Oh, it's 18, because it's a triangle, right? So what we'll do is we can say 18 because it's 1/2 15 feet, 2.4 kips per foot. So half of 2.4 is 1.2. 1.2 times 15 is 18. Now, if that's the case, somebody help me out. What is that dimension? This dimension's 5 feet. It's 15 feet wide, a third over, right? Triangles, the centroid's a third over. So that's 5 feet, which makes this dimension here 10 feet. Now it's just a beam with point loads on it, right? So it's no different than it was before. So I'm going to use the same strategy. I'm going to sum moments at A to determine the reaction at B, sum forces in the vertical direction, determine the reaction at A. So far so good? All right, so help me out. Let's see. All right, so let's sum moments at A. So, summing moments a day, and this is one of the reasons why I kind of like doing the table, is you could just sort of check it off, like a checklist, right? So, do we have to deal with this force? Do we have to deal with this force? Do we have to deal with this force? Left or right side of the table? Left. And how far from A? 5. So 18 times 5. All right. Let's see. So we took care of that, took care of that, took care of that. What about that? Does that generate moment? Left or right? Left. And what side of the what's the moment arm? Sorry. 22.5 feet. All right. What about this BY? Left or right side of the table? And moment arm? 30 feet. And then what do we got? We got the 33. Somebody tell me, what's the moment arm going to be? 41, right? From A, because it's 30 plus 11, and then it's on the left side of the table, right? All right. So let me scroll down a little bit. So what do we got? 18 times 5, that's 90. That's 225. 33 times 41, 1353. And so, what do I got here? What's that sum?
1668.
Do I have a second on that?
Yeah.
And so we'll say foot kips, my little shorthand there, BY times 30 feet. And what's BY? 55.6. Do I have a second on that? We got a positive value. Positive means we assumed the direction was correct. We assumed upward, and it was in fact upward. So that means, by golly gosh, we got 55.6 acting upwards. Last thing we do, we sum forces in the y direction. Remember, when we sum forces in the y direction, all we're doing is we're listing the forces, everything going up and everything going down. We do not multiply them by a distance. We don't say, 18 times something or 10 times something, because we're summing forces, not moments. You multiply because you're summing moments. Okay, so what do we got? We got AX. We don't consider that, so it's going left or right. We've got AY and BY going up, and we know what BY is. And then going down, 18, 10, and 33. Uh, 18 and 33, that's 51, 61 kips. And so 61 minus 55.6, what is that? 6.4, 5.4? 5.4. So AX is 0. AY is 5.4 kips going up. And BY is 55.6 0.6 kips going up. Sometimes I'll just write in my solution A and S as a shorthand for answers. But yeah, there you go. And I mean, look at the values that we got here. We got a really, really tiny reaction for A and a big old reaction for B. But look at the loads, right? The loads are like really concentrated on B. Like they're all the way over here. This 10 kip and 33 kip load are like right there at B. So it kind of makes sense that that reaction is going to be pretty big. I mean, most of the loads are focused that way. So I am going to try and do that as the semester progresses. Is we're going to have some problems and we're going to be doing some analysis. Does the answer make sense? Because if it doesn't make sense, there's probably an error. There's probably an error in the math. But I will say that there's sort of a beauty to a lot of what we do in here, and that is that a lot of the math, a lot of the process is, hold on, let me do this. A lot of the process sort of self-corrects. So like, for example, when you're drawing moment diagrams, you start at 0, and if you do it right, you'll end back at 0. You know, it's same thing with shear diagrams. So it sort of figures itself out. Like when you're doing a truss analysis and you're utilizing method of joints, by the time you get to the last joint, the truss is sort of solved. Like it's already sort of figured out. The last joint, the answers are sort of well known. Okay, I'm going to stop for a second. Any questions? All right, so what we're going to do next time, I think it's what we do is we deal with inclined rollers. So what if the rollers are inclined, or what if the loads are inclined? I think that's next time. And then we start dealing with concentrated moments, fixed supports, internal hinges. So we're going to just, again, for the next few lectures, we're going to take the concepts and we're just going to ratchet it up a little bit, slowly but surely. And by the end, we're going to do some really weird reactions problems. In terms of homework, a similar homework problem, 2 homework problems, kind of like just like what we did today. If you can do this, you can do the homework. I promise I'm not one of those professors where it's like in class the problems are 2 + 2 = 4, and then the homework's like calculate the mass of the sun, you know, or something. I'd really try and not do that. I know you know, we're going to have homeworks that are easy and homeworks that are challenging, but I want the lectures to prepare you for the homework. Otherwise, because to me, the homework is really where you learn this stuff. So doing it is the best way of learning it. Okay, any questions?
Next one is Monday, right?
Monday, same way. So I got everybody's homework on submitted on Blackboard. We'll get that graded hopefully over the weekend. That's all I got. I will see you all on Monday. Go have a wonderful weekend.
You too. All right. I had a question.